Go.
Hello.
Hello, and Mr. Ryan, are you alright? Okay,
Yeah.
go back, go back.
Yeah.
Okay, so today we could talk about another binary search. Not a binary, a tree problem, okay? A tree problem. It could be a binary search tree, a binary tree, or it could be a tree, with multiple kids, right? So let's say 3,
99 kids.
1, yeah. 5, 10. Okay.
There's only 2.
Yeah, binary tree. But it could be many, yeah? It could be many. Let's say it could be many, 7. And then it could be something like that. And it will be, it could be many kids.
2 10s.
So let's say if I want to take the 5 out, and the question is that when you take the 5 out, you need to take all the notes. Yeah, good question. Okay, so it has
Hey,
to be
I
unique.
said 2 10s.
So these notes are unique.
11.
Okay? 11. Okay. So if I want to take the 5 out, you need to tell me how many notes we need to take it out. If you're taking the 5 out, you need to take every single note, every note in its
child.
on each child. Okay. So.
Or children.
Yeah, so you need to tell me it's 5 and 10, okay? Right, 5 and 10. If I take the 5 out, let's say kill it, okay? If I want to kill 5, you need to tell me.
Kill it.
You need to tell me, come on, okay, 5, 10.
I'm killing it.
Okay, good.
That's what you call a kill. Hey,
5,
you
10. Or you can return 10, 5. Or if I want to take a 7 out, so you need to tell me what I
Take
know.
7, 4, 9, and 11.
So what? Don't do it.
Mom, we're gonna take 7, 4, 9, and 11 these away.
Yeah.
Cut them off.
Yeah, okay. We're done, okay. And how about if I take a 3 out?
We just take 3. No, we take all of it.
Yeah, sit down.
Look at the magnet
Yeah.
bit. All of this.
Okay, all of it, okay? But the thing is that you are given the tree, because it might not be the binary tree. You're given a tree like that. You're given this, for example, this tree could be given these nodes as 3, 1, 5, 7, 10, 4, 9, 11, right? This is the node.
You're doing it by breakfast search.
Yeah, could be.
Going
Okay,
each
wait.
level.
Yeah, we're done. Okay, so now look, what's the parent of them? If the node is a root which does not have any parent, we give it its parent is 0. Okay, that's 0 is a special value. Means that look at the root of 3, the parent of 3 is 0, right?
Yeah, we're gonna kill it.
Okay, so the parent of 1 is what?
Parent of 1 is 3.
5.
3.
The 7.
3.
10.
5.
4.
7, 7, 7.
We're done. So you get it, yeah?
7, 7, 7, 7,
Yeah.
7, 7,
So you
7,
look with these two information, the node and their parent. Okay, because we only have distinct numbers. Yeah, we only have unique numbers. So with these two, this.
7, 7,
What can we do about it?
0 plus 3, duplicate it 2 times.
Uh,
Plus 2. Brute forcing.
Brute forcing, yeah, good idea.
Plus 2, duplicate it 2 times.
okay. So we want to take, for example, we want to take the 5 out. So what's your approach? First, we want to take a 5 out. So what's your approach?
Just.
So look, we can go through this list, yeah? Right? Look, we can go through this list and check which parent is 5. Right? Which parent is 5? Whose parent is 5? 10, right? 10 is parent 5, right?
No,
10
5
parent.
and 3.
So look,
And the child is 10.
we want to take this out, yeah? We want to take this out.
That,
Okay, listen to me. We want to take this out. So we go through this array, yeah, to check. We go through this array to check which parent is 5. Which
so
parent
we
is 5?
look at this one.
Yeah, which parent is 5? 10, yeah. We find here, right? And then 10. So 10 then will be here, and then we go through. Sorry.
Oh, okay.
And then 10 will be taken, right? 10 will be taken, but we also need to take any node, right? Here, suppose there's many nodes here, right? So we need to recursively call this function to take the node whose parent is 10, right?
What if that nobody's parents is 10?
Good question. If the nobody's parent is 10, then we just stop, right? For example, the leaf nodes. Leaf nodes, there are no parents. Leaf nodes. Terminal nodes. We also call it terminal nodes. So, because there are no parents. The leaf node does not have any kids. Okay. So in other words, no nodes parents is the leaf node. Okay.
Yeah.
Makes sense? So that's a very straightforward idea, right? We want to take the 5 out. So we go through the array to find out whose parent is this node. And then we add it to the answer. And then we recursively calling the function with the ID whose parent is that, right? Got it? So in this case we can build the answer, right? So let's write it. This is called brute forcing. Brute forcing. But it's not very efficient, right? Why is that? Because every time we need to go through the array to find out whose parent is whose parent is that, right? And we can build it other way. Right? Think about it. How can we speed up this query? So basically, we want to find out whose kids. So what are we doing there? We want to find out whose parent is that the node, right? Look, before we know the node. We have given a node. We can know whose parent is that, right? Because it only has one parent. That's 1 to 1. Many to 1, yeah. So a node can have only one parent, right? We want to find out whose node. We want to find out which. We go through this node. We want to find out. This is n1, n2, could be n3. They are all point their parents on, yeah, right? We go through this array to find out whose parent is p, right? Right? This is not very efficient. Every time we need to go through that again and again, right? So, for example, if a node is like that, 1, 2, 3, 4, right? Yeah, we want to find out 1, right? Yeah, kill 1, right?
Don't kill all.
Yeah, but first of all, we need to go through that 4 nodes again to find out whose immediate parent is 1, right? Okay, and then find out 2, right? Okay, then I need to go through the list again to find out whose parent is 2, right? So I need to do that again.
+4.
And then I need to find 3, yeah, 4, 3. And I need to go through the list again to find out whose parent is 3, yeah?
So +4 +4.
Yeah, you see? +4 +4.
No, why do we need to +4?
I mean, no. What I mean is
because
search.
more notes. No, because in the list, why is like 2 always at the end, 3 always at the end, and then 4 is always at the end because you need to do the whole. So that means it has to be at the end.
No, it doesn't have. Look, how do we build this one? The node is 1, 2, 3, 4. Yeah, 1, 2, 3, 4.
Yeah.
And then the node will be 0, 1, 2, 3, right?
Yeah, but when you get to 2, it's not at the last, so you only +3.
I don't get your question. What do you mean?
Because 3. So you can't do +4. You need to +3 and it's not at the end.
But the thing is, okay, good. That's very good observation. Yeah, but we are talking about the complexities. Okay, so in this case, yeah, you're right. It could be n plus n minus 1 plus n minus 2, right? And plus n minus 2, yeah, because you already found it, right? Yeah. But this is still, there could be n times, yeah. There could be n nodes if there are n nodes, and then you need to do this n times, yeah. Plus. And what's the time complexity for this? n plus 1 times n divided by 2. So that's O(n) squared, right? Yeah, that's O(n) squared. That's the time complexity. Okay. So should we write this first? And then think about it. How can we speed up? Because all we want to do is find out the list of nodes whose parent is P. And how can we do this opposite? Look, can we do this opposite? Huh? Can we do this opposite? So if we do the opposite list, that will be what? Alright? Right?
4, 3, 2, 1.
No. Now we are given the data structure pointing the nodes to
P1.
Yeah, P to the nodes. Yeah, P to the nodes will be n1. And if we can do this, if we can have this kind of data structure, we can easily do traversing the tree, right? What kind of algorithm can we traverse in the tree? Come on, this is the easy answer for you. What kind of
Reverse search, left search.
well done. Okay, so let's do this one by one. Okay, first of all, brute forcing, depth search, and buffer search. Okay, define. Let's just say kill. Okay, kill, and then we have two numbers, parent, and the number to kill. Okay, okay. Kill. So first of all, we need to do what? We need to go through the answer will be. Okay, so if kill equals the parent is 0, then we return it. Yeah? We just return. We just return. Now we have the answer. We want to k, and then we need to do what? For what? For what? So what are we trying to do here? What are we doing here? For what? I in range. We need to go through this P array, right? P array. Ryan, you got a question?
No.
If
You said
pi
I got a question.
if pi, so this is the value parent. If parent equals the k, current k to take away, right? Then I need to answer plus here, and that will be np. But now I will need to take that thing, which is what? P ni, right? Ni, and then return answer. That will be okay. So this is the brute forcing. Oh, look, if k equals 0, that means that's the, you know, that's the root, not the root, okay? If k equals 0, we return because the 0 does not exist. Now, obviously, we need to take the k out, right? To kill the k, right? And then we go through this array. We go through this parent array. And if the parent equals the thing, if the parent equals the thing to take out, right? And I need to take out what? I need to recursively taking out the node. So what does it mean? Look, that's 1, 2, 3, 4, right? So I want to take the one out, right? Right? And then look, answer equals k, right? Now, so answer have at least 1. And I need to go through the element to find out whose parent is 1. Yeah? Whose parent is 1 here? 2 and 5. Right?
You just drew 5 on.
Yeah, I know. 2 and 5. So look at this parent, 2 and 5's parent is k. Is 1. So I need to recursively call this function to take the node 2 and 5 out. Right? Answer plus to answer, and then I return the answer. Okay, so the time complexity as we discussed is O n square, okay? O n square.
Yeah, that's what I said.
Don't repeat what I say, you need to understand, okay?
And I meant.
So look, if we build this function, so look, we have n to p, right? So we want to build p to n. So what kind of data structure can we use to build the parent to the kids? What kind of data structure? The thingy. You know,
Notebook.
Yeah, the notebook. Okay, so look, let's say children, okay? Children equal before dictionary.com. And then because the key is the parent, what's the type of the kid? A parent can have many kids, right? So it could be a list, right? A list, yeah. So now I need to go through the parents, okay? So let's one look the triad, the parents, okay? In what's zip function? Remember? NP. What's zip? What's zip? Remember we talk about a zip. What's zip?
A zip is what?
Zip. Yeah. Zip it together, right? So I zip it N. N is here. P is here.
I don't have a zip.
Look. Zip. Look, N array.
In the coat.
Come on, go back.
Or in the
Sit down. Array, right?
jacket, or I don't know.
Look. N and P. Look at me. N and P. Zip it together. So now C and N will take one each other. So, right?
Yeah.
So look.
Yeah.
And then I need to do what? Children, parent, right? This is parent, right?
Power.
Dot append. because this is a list. Yeah?
That's a pen.
Append C. Okay, got it?
Where did
look.
you get C from?
C is the the zip. I take one element from the nodes and then take one element from the P, C and P from N and P, right? Got it? So in this case, then I can build a parent to the kids array, right? The key is the parent. The kid is the value is the list of the children, right?
Fine.
Am I right? And now with this data structure, I can just easily do the DFS search. Easy, okay? Can you? Yeah. I do this DFS define DFS search. So let's say the root, yeah? Right? And then what? Look, answer at the beginning equals to the root, yeah? Look,
Yeah.
I want to take the root out. Of course, the answer has to include the root, okay? Yeah. And then now I just need to go through its kid. Its kid. What's the? I just need to go through the kid of the root, right? For I in children, yeah, we have these children, yeah. Children, root. And then what do we do? Answer plus equal DFS search I, and then return answer. You see how easy is that? Got it?
Cache.
Take a look. Make sense? Take a
You need
look.
the cache.
We're done. Cache. Okay. Just return cache. First of all, then we can need to return DFS root key, right? Yeah. Okay. You talk about cache. That's a very good point. But actually, it doesn't help much. Why is that? Look, I want to clear 1, 2, 3, 4, 5, 6. Right? If I want to clear 1, right? I'm going downwards. So I need to go through the 2, 3. I just follow this, right? If I cache this, doesn't help because I don't need to visit it again, right? Am I right?
Just checking if you're correct.
Do you understand what I'm talking? Look, when is the cache useful? Because look, if I want to kill 1,
If they're duplicated.
if later I want to call this kill 1 again, but for now I don't need to call it again because look, I want to kill 1 again, and then now I can find from this data structure I can find 2 and 3, right? So then I need to kill 2 and kill 3, right? From kill 3 I need to kill 4 and kill, and from there I will kill 6 and kill 5, right? Take 6, take 5 out. So look, for each function, for each root, I only call 1, so I don't need to put a cache, right? It doesn't help, right? But look, this is the DFS search. Do you understand with this data structure? Am I right? Alright? Make sense?
Yes.
Answer the DFSI. Look, the return is the list, yeah? Okay, look, listen to me. The return, this plus equal is to extend it. You can also do this answer dot extend. It's the same thing, yeah? Extend. Huh? What does it mean? Look, if list is 1, 1 plus 2, 3. Look, this, look, a list of 1 plus 2, 3. That will become a list of 1, 2, 3. Yeah. If the list is A, you can say A dot extend 2, 3. Another list, and still A will become this. It's the same. Okay. Make sense? Okay. With this data structure, we can go use breakfast search. Okay. I'm going to easily write this. Okay. So what kind of data? How can we implement a breakfast search? Remember, we need to use a data structure which is called what? Usually data search is implemented by the recursion. Yeah, recursion have the stack, first in last out, right? And what's the opposite? We need to do the breakfast search. What's the data structure? That is not stack. First in, first in, fast out. Okay.
That's what I said.
So look, let's say 3, 2, 1, 10, 11, 12, 13, 5, 6, 7. Okay, so let's say I want to take a 1 out. What's the breakfast search? 1.
Oh.
So look, 1. You put a 1 in, right? You take the 1 out, and you push it git. Alright, sit down, otherwise people don't see it. You take a 1 out, you push the kids, which is 10, 11, 12. In here, right?
Then you push the babies.
11, 12. Okay? And then now, I take all the kids out from the queue, and I push their kids. So which is 13, 5, 6, 7. Got it?
What kids could have kids?
So the kids, look, this. So this in this way, they will be level by level, okay? Make sense?
Yeah.
Sit there. So look, let's say Q equals, at the beginning we use the DQ, yeah, double N DQ. And at the beginning we have the K, because that's the thing we are going to take it out. And the answer will be, of course, with the K, right? And then Y, Q, Y or Q, or Y, length Q equals 0, it's the same, yeah? Length Q, or length Q bigger than 0, it's the same. YQ, then we want, first of all, we need to take, we can take one at a time, or we can take everything at a time from the Q, right? We talked about this last lesson, yeah? From the Q, breadth search, we can pop one at a time, or we can pop everything of the current elements in the Q, right? So let's say we want to take all the elements, so T equals length Q. And then now I need to take everything out of the Q. For in range T, and then I want to take it out. So which is what? Current equals what? Equals Q. So how can I take it out?
Q dot pop.
Pop what?
Left.
Pop left. Because the Q, the Q, when you take Q, when we take an element out of Q, we take it at the front. When we put the thing in the Q, we put it at the end, which is what? Pop left and append, right? Way down. Okay, let's see.
Pop is taking it away.
Taking it out, right? Taking it out, right? So we take it out, then what do we do? So we take it out, what to do? Then we need to do for I in children, yeah? Because we have a children. Children C. With children C, then we do what? We do what? We do Q dot append. Append I, right? Yeah. Right? So in this case, Q dot append right, yes. But first of all we need to take it. Sorry, there's a problem. Okay. Answer. Right, come on. So we take it out, and then we need to put it here. The answer needs to append because we already taken out, so we append the C, right? Append the C, and then we append the I, and return the answer. Right? So let's go through this again. Answer at the beginning we have nothing to. This is the list to store the number, to store the nodes to take out to kill. Okay.
Yes.
Why the queue still has element? Yeah. Then this is the number of elements in the queue. Then we need to pop them out all at once. Okay. Then we take one out, the C. Then we put it in the answer. When we take the CR, we need to append its kids, right, back to the queue. So let's wait it for I in children C. Yeah. Children, here we be here. The key value pairs. The key is the parent. The value is the list of the children rows. Okay. Then we append the I back into the queue. Okay. So what's the time complexity of the depth search and breadth search? If there are n nodes in a tree. The brute force is O(n) squared. Yeah? We talk about that because every time we need to go through that thing to find out why is it O(n) squared, because we may have to go through the list to find out whose parents, which nodes the parents as the parent of that, like the target, right? So that's n times, and for each node it has there are n nodes, so there will be n squared. But for this one, we already built it, so we can just follow this. What's the time complexity? Come on, if I take this out, I just need to visit all these ones. O(n). What both are the O(n), right? What's the space complexity? Are we using any space? O(n), yes. Okay, be confident, okay? Make sense? Okay. Any questions so far?
No!
Okay, so that's it for today. Good job.
Bye!
Bye bye.